So we are discussing ZigBee protocol, and ZigBee uses pretty much standard stack, protocol stack with network layer, transport layer, application layer with some different names. And so we are on the top layer today, which is application layer. The transport layer is called application support layer. But starting with the application layer, on the application layer you have many applications, and each application is called an endpoint. Sometimes it can get confusing. End node is the hardware and endpoint is the software. Okay, so each end node can have up to 250 application objects, means endpoints. So these endpoints are like port numbers in TCP, right? So you have 250 endpoints per end node. And so if you have this remote control switch controlling the light, you are going from endpoint 1 to endpoint 6 on this node. And then there is a management object which is called GDO, ZigBee device object, and that basically does most of the things which are required for security, etc., etc. And then application support layer, which and network layer and other things we'll discuss in a minute. But application support layer, as I said, is the transport layer, network layer is the routing layer. So one more time, application layer consists of the points and the GDO object, only two items, two sets of items, because you have these many objects, up to 240 of them, and then you have the GDO and then interface between them. 56 endpoints theoretically, but only 240 are allowed, and GDO itself is a endpoint 0, and 41 to 254 are reserved, so you get from 1 to 240. 255 is the broadcast. So that's all the port numbers you have here. Okay. Each endpoint has one application profile. So it might say that on port number or endpoint number 6, I'm running a light. You could be running a light on some other port number as well. And so ZigBee forum has defined a number of profiles, just like Bluetooth. They have defined a profile, a light profile, a switch profile, and so on and so forth. And each profile requires a number of data items. Each data item is called an attribute. So that name is a little bit confusing to me. Attribute looks like property, but this is the object. Okay, so the object is a data object, integer, number, or something, but this is called an attribute because people think integer is an attribute, which it is, but we are referring to the number. So the number is an attribute, which is it could be an integer or or real or floating or whatever. So each profile requires a number of data items. Each data item is called an attribute and is assigned a 16-bit ID. So when you say I'm sending you data type 1, you know that data type 1 is integer. So how to read it? If I say data type 2 and I'm not using the actual data type here, just an example. So everybody knows what they are talking about, what type of data it is. Okay. So this is all there in the application layer. Basically, there are lots of profiles which we will not go into. Actually, we might go into it later on just as a list. But now the data items come in a group, because you generally don't just use one item, you use a group of items, so they are called clusters. And so the group of data items is called a cluster, and each cluster is assigned a 16-bit ID. So just like a data item, you say, well, I'm going to send you an integer plus I'm going to send you the power, I'm going to send you the size, this and that. All of those are clustered together into one cluster. Yeah, go ahead.
Does the data item include the actual data or just the type of what the data is?
So they have a standardized type, and when you send something, first thing you say is this is the type, this is the length, and this is the value, TLV, right? So the type is standard, so anybody can understand what is the type is. Understand that part? So TLV, only T is standardized.
So does the data admin include the whole TLB?
When you send, but when you define your program or you design your interfaces, then you need to know the key. So that is standardized. We are just talking about right now the standardization part. When you implement, you can't just implement say 16, right? Good. Now the cluster is this whole group, all right, and they have a number of libraries for clusters. For example, they have a library for let's say smart grid, or for light control, or for anything, right? So there are libraries which have also been standardized. And then there is general cluster library, which is a generic kind of thing, which contains many of the things such as on-off, level control, alarms, etc., which are used in the remote control. And that's how the ZigBee started life actually as a remote control in homes. Remote control of lights in homes. And then binding, the process of establishing the logical relationship, parent to child, etc., etc. So when you have a network, you have the coordinator, you have the routers, you have the leads. That relationship is binding. Okay, GDO. GDO uses device and service discovery commands to discover the details about the other devices. So this is basically, in some sense, control and management plane combined. Okay. For example, service discovery, device discovery is control, because without controlling, you can't really control anything. You cannot really have a network. So this is not so much of management, but they just use the same name. So this is GDO is device discovery, service discovery. Binding and unbinding means finding a parent, finding a child, getting rid of them, and then using network management commands for route discovery, etc., and the link quality. So everything that is required in addition to data transfer is put into this object. All right, so let's be sure. So people just use the standard application profiles, and then most of the network operation is done from here. Management and control from here. So we haven't talked about any lower layers, but we have just finished this layer. This is just the interface. The application objects can talk to the GDO. Okay. Application profiles. So now they have lots of application profiles. The top one being smart energy, which is actually probably the latest one. This is not in the time order because probably home automation came first. Smart energy, electrical, gas, water meter reading, commercial building automation, smoke detectors, lights, they're all automated nowadays. So in a building, you might have 2,000 smoke detectors, right? Just imagine how many floors and how many rooms per floor. And if one goes off, everybody has to be told. So everything has to be networked. And this is the network. And hospital care, monitor blood pressure, heart rate, telecom applications, mobile phones. And I haven't really seen much mobile phone ZigBee, but there might be some. Remote control for consumer electronics. So recently they started this one, television remote control, etc. with radio. So previously your remote control, TV remote control worked only in the same room. Now it works from the bedroom or anywhere in the house. That is radio, as opposed to infrared, light. Industrial process monitoring and control, temperature, RFID positions, and so there are many profiles, as you can imagine, for sensor applications. So we are going to move to the next layer. Before I go to the next layer, any question about applications? Okay. Application support layer is actually there is not much. It has three parts, which is a standard part of all the other three layers: data part, management part, and the information base. These are new names for, AIB could be called MIB, management information base. Everything in the world has a MIB, right? When we teach you the 473 management chapter, we tell you that every object, whether it is a router, whether it is a network layer, whether it is an application, everything needs a management information base, which is the database that contains all the information as to what you can ask about that particular object. So APS has an APS information base. So that is just straightforward. We won't discuss it anymore. Management entity is basically the one that processes those commands. So if you say, please read me this counter or please write this counter, that is the management entity. So this is not much to talk about. Data entity is the one that we'll talk about, and that is where you send the frames from applications to the network layer. So basically, just like a transport will have a application format, frame format, APS has a frame format. And some of the key things that I wanted to highlight was, which are noted here. Basically, again, it's not important to know the exact order and all that, but the thing is, you have to know what is really, can be done and what cannot be done. So, for example, there is a fragmentation field here, which will come to a minute, and if you think that it cannot do fragmentation, that will be bad. So you really have to know that, yeah, it is this particular thing allows fragmentation, or it doesn't allow fragmentation. Some of the key overall features you have to know. So now let's start with this. You have you have frame control, which is 8-bit. Then there might be or may not be a destination endpoint. Now remember, this is endpoint, those 240 applications. And then there might be a group address, means it is going to many endpoints. There may or may not be 0 or 8-bit. 0 or 16-bit of cluster ID, 0 or 8-bit of profile ID. Then source endpoint, 8 bits. So this is just like a port number, right? The beginning port number and the end port number. And then you have the APS counter, which we'll discuss. Then there is a possibility of having an extended header, 0 or 24-bit. Remember, this is a low speed protocol, some 100 kilobits something per second, right? So every bit is optional. Bits are very expensive here. And so it is all being pushed to, that's why we have all these optional fields. And that is a common design technique. Low speed, you have this variable bit length fields. High speed, you want fixed size fields. Payload. Alright, so let's go back to the frame control. Frame control first tells whether it is a data, command, or ACK. So every packet is acknowledged. Right? So that is where data is clearly what you want to send. Command is something that needs to be done, which is, I want to associate with you, I want to, whatever you want to do with me, and which is not related to data, right? That is command. Delivery mode is unicast, indirect, broadcast, and group addressing. Okay, so we'll talk about indirect in a minute, but unicast, and broadcast, and group addressing should be clear. Group addressing is a special case of broadcast. Actually, group addressing is multicast. ACK format. ACK format is simply 1 bit. So all it says is whether the ACK is there or not, 0 or 1, present or not present. So essentially the name is misnomer. Security is there or not there. ACK request, whether I want the ACK or not. So the ACK is optional. And the header is present or not, extended header is present or not, the last one. So these 4 bits simply indicate what is missing in the main frame, right? Or it is there or not. Now, if there is an extended header, then there are 8 bits in the beginning, of which only 2 are used. 6 are reserved, right? So there is extended frame control. The 2 bits are used for not fragmented, first fragments, other fragment, and reserved. This is the same way like it is done in IP. Your first fragment field, more bit, just 1 bit, more bit, and then basically, you end, right? So when there is no more. So this is the same way, not fragmented. So that is basically, this is the beginning and the end. Otherwise, this is the first and this is the intermediate one. Block number would be basically, if it is fragmented, then you tell them what fragment it is and the acknowledgement for what block. Yeah.
How do you determine the datagram integrity?
How do you determine the datagram integrity? Right. So basically, somewhere in the payload, and I haven't verified this, they will have security. Security actually in somewhere. So here's the thing: the security could do both integrity and privacy, right? CIA. So I is integrity. So it could do integrity right there. But I think integrity is required even if you don't need security sometimes, just to be sure, right? And the simple integrity is CRC, which is not secure. You can easily change a packet and change the CRC, so it's not secure. But there are secure ways of making integration. Making integrity checks. Yeah.
I think ZigBee actually uses lower layer security, maybe layer 2 security.
I'm sorry?
I'm pretty sure ZigBee uses a lot of layer 2 security.
No. In this layer, there is security right here. Right? So all it is saying is that there is a security bit. If that is there, then somewhere there is a whole security data. Right? So all I said was that we don't have that field right now in front of us. So we really don't know exactly what is in that field. But I mean, all they say is AES, 128 with whatever mode. So in that mode, actually, when you have security, then integrity is automatically included. Because integrity means nobody can change the data. If somebody changes the data, you know it. Right? So security includes integrity. Integrity does not include security. Yeah, go ahead.
Actually, ZigBee uses AES 128
Yeah.
CBC
Yeah.
which is the counter CBC MAC.
Right. Okay, so right there, CBC MAC. MAC is authentication code, right? Message authentication code. So that is integrity right there. MAC is another name for CRC. CRC is a method of integrity. Okay, good. Thank you. Anything else? All right. So let's see. ACK format, as I said, one means all of this are present. One means security, one means enable security. ACK request, please ACK. External header is present. ACK acknowledgement for a fragmented frame. That was the last bit here, last field here, ACK. This is the acknowledgement for a fragmented frame that I got your fragment number 5. Destination endpoint is that application. Cluster ID, profile ID, as we talked about. These are the applications and the data groups. And then the APS counter is simply a frame sequence number. So when you send a frame, you might send 4, 5, 6, 7. Frame number 4 might get into many fragments. So then the sequence number will remain the same in those fragments. Okay. So this is the sequence number. All fragments have the same APS counter value. All right. The ACKs have a slightly different, and the command frames have a slightly different frame format. The one that I showed you here was the data. So the ACKs do not have group address field because you don't ask for ACK if you are going to send it to many people. You will be just inundated. And then you do not, you cannot even, basically, so that is the thing. So basically you have frame control, endpoint, cluster ID, etc., etc., and the external header will have the ACK value. Command frames can go to a group. So you could ask many of them to join you or do whatever you want to do with them. So that is a command. And the command frames will have a group address, and the rest of them are somewhat straightforward, similar. So the main thing to remember here is that when there is a group, a multicast, then you don't do the ACKs, and the commands and data can get the ACK. All right, so much about transport. And this is very much standard stuff. In IP, these things are done at different layer. So for example, fragmentation is not done at the transport layer, it is done at the IP layer. The reassembly is done at the transport layer, right, in TCP IP. Here, this layer does both the fragmentation and reassembly. The network layer only deals with the fragments. Okay, Now, network layer has the same three things. It has a data entity, it has a management entity, and it has an information base. Information base is simply the MIB. And so, again, we don't need to discuss much. Management entity has commands. We will discuss some neighbor discovery, route discovery, etc. And the data entity is, it simply makes the PDU out of SDU. Right? By now you know PDU, SDU. So it takes the fragments and puts some more headers on it and then sends it out. Again, the header looks very similar, somewhat repeated in some sense, but you have frame control, destination address, source address, radius, and we'll talk about that. Radius is actually a name for hop limit or time to live. So that is radius, and then you have sequence number for the fragment or whatever it is now here. Destination address, source address, multicast control, and so on and so forth. These look very similar to what you will have in IP packet, except that most of the things are optional. So 0 through 64, 0 through 64, 0 through 8, these are all means that they may or may not be there. And therefore, we have 1 bits here that will indicate whether they are there or not in the frame control. So that's a standard method of variable length flags, variable length headers. Okay, so frame control is 16-bit. 2 bits is the frame type, data command. Route means please do not discover route for this packet. So when you send a packet, and we'll see in a minute, there are 2 options. Either you can put the destination address or you can put the destination route. You see, this is called source route here, which is actually the route to the destination. This might be whole field. It will say, well, go from here to 270, from 270 take 170, then go to the airport. The whole directions could be there. That is source route. Or it could be just destination that go to the airport. So in either case, if suppose on the way you find that you don't know how to get to the airport, just come back, give me an error that I don't know how to get there. No route discovery. Okay? So you cannot find it on your own. Second thing is force discovery. Well, find the route. All right? And if no route, discover. So this is kind of the gentle discovery. So force discovery means forget all your previous one, flush your caches, find the latest route, because that could have changed. So that is the option for the route discovery. Now let's see the standard fields. Frame type, we already talked about. Protocol version, standard thing. Discover route, we talked about. Multicast flag simply says that this thing is there. Security will say that the security is there somewhere. Source route says that the source route is there, and that is actually probably, yeah, right here, source route, variable length field. Destination IP address is there, source IP address is there. So sometimes you really need to use the full 64-bit address, particularly when you're binding, unbinding, joining, leaving, things like that. So then that is, these bits will indicate whether those fields are there. Okay. Now, I said I already talked about radius. Radius is how far should it go? How many hops should it go? So this is the hop limit, also called time to live, TTL. Right? Now let's see. So source and destination address, sequence number, everything else is clear. Any questions about any of the fields? Okay, so multicast flag means multicast present, broadcast frame. Now broadcast frame could have, so there's not just one broadcast address, they have listed 4 here. So actually I would call them multicast, but, so this is real broadcast, FFFF, all devices. FFD is those devices which are on. FFC is coordinators and routers. FFB is low power routers. Okay. So they have 2 kinds of routers here, routers and low power routers. And we didn't see that discussion before. Basically, it looks like that low power routers will turn off and these routers probably will never turn off. But anyway, so these three are technically multicast, but they are called here broadcast. Then source route contains the whole route, and this is variable length. Depending upon how many hops you are going, you have to put on every hop where to go. Radius is the hop limit, destination source address, security field, and multicast control field, whether it is a multicast address. Alright, so much about the frames. Now we talk about what we said here was the neighbor discovery and finding the routes, etc. So this is the routing part. So when you learn about IP, you learn about IP and OSPF, right? IP is the frame forwarding, as we call it. OSPF is routing, in the sense that finding the route, right? So same way, there are two parts here. This part that I'm going to talk about is finding the routes. What we just finished talking was just frame forwarding. Forwarding and routing. So, so each node carries a table like this for each neighbor. What is their IEEE 64-bit address? What is their short address? What type of device it is? Whether it sleeps? And what is my relationship, whether father, son, children, not father, parent or child. Transmission failure. Basically, it says that, yeah, it was there, but I have already had one failure, two failures, and sometime later it will be just thrown out. Transmission failure, link quality. This is another metric. Basically, if I get, whenever you get these coding, the coding will tell you how many errors you are getting, and that will give you the link quality idea. And that is maintained here, that okay, the link quality, we are getting almost like 30% or 10% or 5% or 10 raised to minus 3 error rate. So that is the link quality. And link quality is related to cost. In the wired network, for example, in the IP networks, the cost is related to the speed. If you put a 100 megabit Ethernet and then you put a gigabit Ethernet, the cost is different. And in your routing table, which you can see by saying route print, you see the costs are different. For wireless, there is a different cost. For Ethernet, there is a different cost. For 100 megabit, there is a different cost. For gigabit, there is a different cost. Similarly, here the cost is related to the quality. And then hops from the coordinator. So basically, this is the depth. Permits new joins. So whether if it is a router, then it will permit new join, and logical channel number is channel at which the neighbor is operating. So there are 5 megahertz, 20 channels, actually, right? 80 megahertz total. So this is the one that says, well, I talked to him on 4, channel 4. All right. So let's see. The relationship is parent, child, sibling, previous child. Wow. And then unauthenticated child. They have all kinds of children. Basically, these are different stages. You start out as an unauthenticated, then authenticate yourself, and you become a child. And then you become adult, and you become a router. Then you become a previous child. So anyway, you have a sibling. Alright, so basically you are trying to make the whole graph, which is the tree. Now here comes the really interesting part. Now you guys have been looking for some mathematical stuff, so this is the mathematical stuff. Okay? You won't miss any equations anymore. So ZigBee address assignment. So now we have a network and we want to give everybody 16-bit addresses. There are two ways to do it. The old way is this one. This is called distributed method. The new way is random method. You just pick out of the air and you give it to them. That works. And in fact, it's better in some sense. But the old way is that you want to really keep a very compact space and you want to divide it very wisely. So if I have 15 children, I have to worry about 15 addresses and I have to worry how they connected, how they get there and all that. Right? And I have to give authority to people to give to other people, because the routers, they're not going to ask me whether I can give him 13, or not. I have to tell the routers that you have the authority for 13 to 17. That's why it's complicated. That's why it has been given up. But it is mathematical enough, so I'm going to put it here. But it is used. I mean, in the sense that it is not given up. This is just up to 2007. After 2007, they came in the Pro version, in which they don't use it anymore. So, each node gets a unique 16-bit address, and this is the distributed scheme. It is good for the tree structure. Each child is allocated a sub-range. So, if I have 20 to 35, 15 addresses to give, I will give to the first child, okay, you have half of the range, you have the other half of the range, if there are 2 children. If there are 3 children, I have to give them 1/3, 1/3, 1/3, something like that, right? So that is the scheme we are going to talk about. So each child is allocated a sub-range of addresses, and beforehand we have to decide what is the maximum depth could be, whether children could have grandchildren. So we have to decide maximum number of children per parent, CM, and maximum number of routers, RM. Right? An address of the nth child is parent's address. Child is, actually I should have put the equal to sign here. Address of the nth child equal to parent's address plus n minus 1 C skip D. So this is a value that we are going to calculate, and I'm going to go through the whole example so it will become clearer later. But basically D is the depth and this is the range, sub-range. And the sub-range at the depth D is calculated by this formula. Now how all this came about? Basically it's very simple math. By the time you are done, it's very straightforward, but when you have to write paper, you have to write equations like this, and that's what it is all about, is that they have written all these equations. Simply at the end you will figure out that, okay, if you have 4 routers and you have 24, just divide by 4 and then get 6 to each of them, except you have to make sure that the router gets some, you have to make sure that you get some address left for yourself, otherwise you just give them to everybody, then you have nothing left for yourself. So that's all these equations are making sure, is that all your children, grandchildren get the addresses. Okay? Now the equation looks too complex. I'm going to go into the example. So here we decided that we want to have 2 level of depth of 2. We will have coordinator, router, and then the leaves. No more. So the maximum depth is 2. Come back here and see what is maximum depth, is LM. So LM is 2. Number of routers is 4. We decided that we will never have more than 4 routers. Now this is where you can see the limiting. If suppose tomorrow you need to put the 5th router, you got to renumber everything and reset the button on everything. Right? So we decided the number of routers is 4. CM is 3. Each router can have maximum 3 children. Actually, it seems to be already violating that the coordinator has 4 children. But anyway, so let's say we decided the coordinator can have 4 routers, but each router can have 3 children. Alright? So this is the first thing. You have to somehow put the right value for the symbols. LM is 2, RM is 4, CM is 3. CM is the children, RM is the router, and LM is 2. Next time I will just remove the letter M. We don't need M for anything. So L is 2, R is 4, and C is 3. At the coordinator, the depth is 0. At the router, the depth is 1. At the leaf, the depth is 2, and so on and so forth. You keep going, depth increasing. Yeah.
Should that be a 4 in the denominator instead of a 3 for the RM?
Yeah, it should be 4. So we are going to just put those symbols in the formula. 1 plus CM, CM is 3, RM is 4, CM, RM is 3 and 4, LM is 2. Okay, you see, this is why, this is the thing. I don't think you need any subscript anywhere. I would get rid of all subscripts and make the life easier. But anyway, so 4 raised to this, and you just put up the formula and you come up with the number 6. So everybody should get a range of 6 from the coordinator. So what it's saying is that if the coordinator decides that his address is 1010 decimal, then it should add 6 for every different child. First child it will give 11, second child it will give 6 more, so it will give 17, 5 more actually, so it will give 17 to second child. That means the first child actually has the range from 11 through 16, out of which 11 it will take and then give out 12 through 16 to its children. Right? Then the third child will get 6 more, which is 23. The fourth child will get 6 more, 29. The coordinator is done. Now it's the children's business to figure out how to give next. Alright, so at least now you should understand this whole thing about formula. This formula, all it tells you how many addresses this whole tree can contain. That's all. Yeah.
Sorry, if you just lost me for a bit. Look at router 1, you said the child can address 12 through 16, but you mentioned that the router can only have 3 children. So why so many additional addresses?
Yeah. So 1, 2, 3, 4 plus 1, sorry, 3 plus 1 is 4 addresses is all it needs.
It should be 4 now.
Okay, so here if you put 4, let's see, maybe I did the calculation wrong. If you put the 4 here, what will happen? Okay, so this is 4 raised to 1 is 4, 12, 16, minus 12 is on the top, right? Minus 12 divided by minus 3 is 4. Okay, so redo the whole example.
So you can also simplify the RM greater than 1 case with a decent amount, so it's more friendly.
RM greater than?
Greater than 1, that case in the equations. So what we have there, you can simplify that so it looks nicer. If you pull the 1 minus RM
On the top? Yeah. I can see some calculation. See, first of all, I'll tell you what I found wrong about this formula. Both the numerator and denominator are negative, which is kind of counterintuitive. I would have put Rm minus 1 in the denominator, and the numerator would be just, then you will get at least 12, right? So that is one thing. Second thing is the subscript stuff. There is no need for any subscript here, right? And then the symbols themselves are not very intuitive, L, R, and C. I could have called them depth, maximum depth, YL. Right? There is no L in maximum depth. R is okay. C is children, maybe okay. So there is some work to be done here, but right now it's coming straight out of a book. The reference is here. You have to read that book. Somewhere here in the next few slides there is a reference. Alright, so we found out that this is number 4, and these numbers will then change, and then you will get very compact schemes. So actually, here's the thing. I don't think I changed the example from the book. So there's a bug in the book too. But let's just do the second calculation. At the second level, D is 1. So the formula remains the same, except that here D equal to 1 you put. And you keep going. Yeah. Anyway, you put D equal to 1 and everything else is same, and then this RM is again mistaken and whatever. But you will get out 1 anyway in this case. And this is universal, because once you don't have any more children, you give every children 1. Right? At the last level. So here you get a 1. So then this router gives out, if it gets 11, it gives 12 and 13, 18, 19, and so on and so forth. And so basically these equations simply explain that each router you add 6, 11 plus 6. There is a mistake, 11 plus 12, 11 plus 18, and so on and so forth. Alright, so now you can assign the addresses to children. Right? So there is one problem, there is one homework. Right there. Okay, homework number 13A, which would be due next Monday. Any question about this scheme? All right, so now the next address assignment. The latest method is stochastic address assignment, and this is straightforward. You just draw a random number, just like when you give your son a name or daughter a name, you don't have to go and ask 15 people, just draw a random number and there is the name. And that's how it is. If there is some confusion, you probably give, if there are two people with the same name in the family, then you go back and say, okay, all right, this is a different name. So that's what they do here. Is random number assignment. You announce to the family that there is a new child with this number, and if there is somebody else already there, you give the child a new number. That's the end. All right, now we come to the routing. So far we have just given the names. Now we have to do the routing. And interestingly enough, ZigBee is an ad hoc network. In the wireless course, we used to give a whole lecture on ad hoc networks, in which we used to talk about many routing schemes. This time probably we'll not get to that because I'm going to talk about the key ones right here in ZigBee, and then one or two are left, which you can figure it out later on if you need to. But this is the rest of this lecture is ad hoc routing. Okay. So we'll talk about one of the two key ones, which are actually three key ones here, which are used here. And actually, to tell you the fact, there are four of them, but AODV and DSR is the one which are generally part of most lectures on ad hoc networking. There are RFCs on these. These are quite standard things to do. And so we will talk about them, and then there's a tree-hierarchical routing and many-to-one routing, which is required in the sensor networks. So AODV. AODV stands for ad hoc, on-demand, distance vector routing. Now, how many people know what is a distance vector? Yeah, what is it?
Isn't easy to know the algorithms.
Okay, that's very good. You're getting there. Anybody else? What is the opposite of distance vector? Link state. Good. So that's what it is that, thank you. Thank you. So basically there are two schemes here, two competition. This is a distance vector one, and there is something called OLSR, which is link state. This is like OSPF and whatever the opposite was. So this is a distance vector. In the distance vector, you basically, in the link state, what happens is in link state, you just tell about your neighbors to the world. In the distance vector, you tell about the world to your neighbors. Okay, it's the same information, except that in distance vector, you send so many big vectors to a small number of people, whereas in the link state, you send very small vectors to a large number of people. So that is first thing, this is a distance vector, starting from the back. Second thing, this is on demand. On demand means if nobody talks, nobody needs a route, nothing happens on the network. So you don't just start the power and then say, okay, let's find out. Yeah, you find out so here's the thing though, I mean, you do have to find out your parents and children and everything else. But after that, the network remains quiet, except maybe for hellos. But the network remains quiet, so you don't have to find out the routing until needed. The reason you don't need to find out routing until it is needed is because the routing may have changed. If you find out the route today and need it tomorrow, what good is it? No good. So you find out tomorrow when you need it. So this is on demand. Opposite of this is we call proactive. This is reactive. Proactive means you find out the path just in case you need it. You are ready. Then your message goes fast. With reactive, your message may be delayed. So there is a good and bad. So this is reactive. Routing table. Now this is another thing about AODV. So we will talk about two different methods, AODV and DSR. In the AODV, all you know is the next hop. Just like OSPF, all you know is the next hop. You don't know the complete route. So you know that to get to the airport, you have to take 170. That's all you know. What happens after that is 170's problem. But so this is not a total route, just the next hop. So what you do is for each destination, you keep the sequence number which says, well, the destination at, actually this is not exactly the time, but it is something that is always increasing, so it is like a time, but not clock time. So it's for the destination, for the airport, the route number, not the route number, the information number 15 says that I should go to 170. Now, if you find expression number 16, then you know that is more better information, right? Because 16 is better in time than 15. So it is a sequence number is what is a time stamp, but it is not clock time. All right, and wherever you find this number from, they will just keep increasing every time. So if you ask them again, they will say 17, 18, 19. So you know that this is better, and this is the later information. This is the recent information. All right, so it doesn't have to be clock time, it is just increasing time. So that's why it's called sequence number, because it's just like a sequence. All right, so now you know sequence number. So the next node, the destination, the next node, the sequence number. Now the sequence number really belongs to the destination, not to the next node. So the destination for airport, what is the best information I have, what is the best sequence number I have. Okay? And then when you want to get a discovery, you flood a route request to all neighbors. Suppose I don't have a route to the destination, so I will ask all my neighbors, please tell me if you know the route to the airport or whatever I want to go to, right? So neighbors broadcast to their neighbors. If the neighbors don't know, they will tell their neighbors. Now the request is like this. Source, who is asking? So my address will be there in all the requests if I am the starting point. So this is not the address of the neighbor or anything. This is my address from beginning to the end. Request ID, this is my request number 15. So if I send 16 and I get answer for 15, I know that this is old answer or old request. So I have a request ID. I have a destination address that I want to find. I have my source sequence number. So I have a clock too, right? So I put that, okay, so at time 15, which is not a clock time, I ask this question. And the destination sequence number, and that I already know 13 about the destination. Can you give me better than 13? Right? It could be 0, means I have no idea. Just tell me anything. So there are two timestamps here, source timestamp and the destination timestamp. And hop count. I don't want to go more than 5 hops. So this is the hop limit, this is the time to live. Sorry. No, I'm sorry. This is just a count. I mean, this is not a limit. So basically at every hop, it is increases by 1. So on the first hop, I will start with 0 and then 1 and 2 and 1, 2, 3. So this is just measure the destination. When the answer comes back, you know that the destination is 10 hops away. So this is not a limit. This is just a count. All right. Any question about any of these fields? Yeah.
Actually, it's just one question, I guess. What's the difference between an ad hoc network and a wireless mesh network? If it would be used in wireless mesh as well.
Right. Okay. So we define these 3 terms right here. These terms are often confused. Multi-hop, ad hoc, and mesh. Okay? And these are not identical. You can have a mesh network, such as our highway network is a mesh, but it is not ad hoc. You will find the same highway tomorrow as today. Mostly. Right? But the air network is ad hoc. So you understand? Ad hoc is basically where no fixed topology. That is what distinguishes it. If it is fixed, it could be mesh or not mesh. Right? It could be a tree. So that you know how to recognize a mesh from a ad hoc. And multi-hop. Multi-hop and actually mesh are again confused because they are really confusing in the sense that mesh is a topology. So this is a mesh topology opposed to tree topology. Right? And multi-hop means that you just go more than one hop to go from destination to the source, right? Which is always the case. I mean, you hardly ever go one hop, right? Unless you're on Bluetooth. But the thing is, the confusion happens because we talk about mesh routing and mesh topology. So far we have talked about mesh topology, not about mesh routing. Mesh routing means the end nodes do the routing. So if we had a mesh routing here, you would be as much responsible as, I or anybody else who is a router to forward the packets. Suppose a homeowner association or home neighborhood has a mesh routing, each owner will have to put some of the electricity bill for other friends, for other neighbors. That is mesh routing. So you could have a mesh network without mesh routing, which is generally the case, right? Because the electric company will put their routers, and the phone company will put their routers, and they take care of everybody. You don't take care of anybody, right? So the mesh routing is very uncommon. Mesh topology is very common. Right? Because mesh routing is basically what do I get out of this? That's kind of question people ask. I just use network 1 hour a day and I'm going to put the electricity bill for 24 hours? No. So mesh routing, where mesh connectivity doesn't make any difference. Electricity, so I understand the difference between two. So the mesh routing, mesh topology, ad hoc topology, and multi-hop is again basically a router. Basically is the routing. So because the routing and the topology are intermixed, you get confused. All right. AODV. So now we are back to this thing. So basically we have a timestamp and the source and the destination address, and there's a request ID which is actually somewhat similar to timestamp, but basically it is a different number. All right. Now request ID is this RREC sequential number. So this is my request number 1, 2, 3, 4, 5, like that. Used to discard the duplicates. And then source sequence number is the clock. Destination sequence number is the clock. And if you don't know, then destination is 0. So you just give me any information you have. Intermediate net can reply to RREC only if they have a route to destination with a higher sequence number. So if you're asking for 13 and somebody already has 13 or 14, they can send it to you. It doesn't have to go to the destination. All right. And they will send it by RREC. Route reply, which comes back unicast, and this has to be remembered. It's unicast. So while the RREP is broadcast, RREC is broadcast, RREP is unicast. So it comes back straight from wherever it is to each source. On the reverse path. And it will have the source address, basically who asked for it, the destination for whom, what is the destination sequence number I have, what is the hop count, and what is the lifetime. Lifetime is simply how long is this good for. Every information has a time limit. So if it is coming from the destination, let's say anybody intermediate didn't know it, it went all the way to destination, the destination will put a lifetime on it. Look, I'm going to move tomorrow, so don't use it tomorrow. I'm going to be gone in an hour, so that's the time limit. Okay? Destination sequence number is the destination's counter. Lifetime indicates how long is valid. Intermediate nodes record from both RREP and RREC if it has a lower cost path, and that gives you the reverse path. So that's another thing to remember. It's not just forwarding, also looking and recording. So when you send a request, you know that the request came from there, so you know that the path to the previous hop, right? And when you send it, so basically, so you keep recording both. When the answer comes back, you look at the answer. Oh, the shortest path to 10 is this. So here it is. I'm going to write in my table. So that is an optimization which is done. So then when the intermediate nodes need the same destination, they don't have to start the whole process all over again. Somebody has already done it. right? So they record from both. So here are few things to remember, okay? Because these are the high level things. Everything else you can forget, but this has to be in the brain. First of all, requests are broadcast, replies are unicast. Second thing is everything has a time stamp and a lifetime. Third thing is that you learn from both. The requests as they are going, you remember the reverse path, and the responses when they are coming, you remember this forward path. Intermediate node record from both RREP and RREC. Backward route destination is recorded if sequence number is higher or if the sequence number is same and the hops are lower. So when you get something and somebody says that, you had previously remembered that, okay, for the destination number 10, my hops are 5. Remember that table? Now somebody gives you that, oh, destination number 10 is at 4 hops from you. Then you have to erase the previous information, put the new information there. Provided this is either new information or at least the same time. Right? So that's another rule, is that if it is the same and lower hop are higher information. Suppose you have 5 there and somebody sends you next day information and says it is 6. Sorry, I knew 5 yesterday, but it's no good today. I got to change it. So if the time is higher, you just change it. If the time is same, then you see if the information is better. Backward route sequence number is higher. All entries are timed out, and AODV supports only symmetric links. So we assume that the cast from you to me to you and you to me is same, which is never the case, by the way. I will tell you why. Because let's say I am a big node with lots of money invested, very high sensitivity, I can read minus 100 dBm. And here is a cheap node that can read only minus 10 dBm. Right? When I send to them, they get lots of errors. When they send to me, I get no errors. Right? So the error rate, the link quality depends upon the receiver, which could be different. But here the cost is same. 1 hop is 1 hop. There are protocols and there are extensions which talk about asymmetric links. We will not go into those. Just, if you need to really design a protocol or product or whatever it is, then you can go ahead and think about it. But this is symmetric, and in fact not even taking, even though they said here, remember the cost is related to the link quality. But every example that I've seen, the books don't discuss it. Now you'll have to extend it, or you have to find some other place to find out what happens if the costs are different. Now it's not as the hop count, then you will have to have cost, total cost. It's the hop count there, right? You have to add that hop cost, because right now we just add 1. So now let me give you the example, AODV example. Now node 1 wants to find the path for node 10. It doesn't know it. It has no information. The network just initialized. Nobody knows anything. So node 1 says to who? 2, 3, and 4. Can you please find a route to 10 with a number greater than 0? 2 will tell all its neighbors, which includes 1, and this is strange. It just broadcasts, so it doesn't even remember when it gets the thing, because there is no route in the request. In this case, it doesn't know where it came from, which actually it could remember at least for a second, but it doesn't know, so it sends it to 1, 5, and 7, and 5 will send to 2, 3, 8, 9, and so on and so forth. To all your neighbors, you just broadcast. Of course, you will get a duplicate and you can reject it because you remember that one for whatever reason. And that's all is repeated. That brings us to this table. Now, there could be some errors in this table, and I would appreciate your debugging it, because I spent last night 2 hours per table making 4 tables like this, 2 for me to explain to you and 2 for the homework, or you to explain to me. And it's 2 hours per table. So I won't be surprised if there are some bugs. But, in fact, this is not from book. I mean, this is basically my understanding of AODV. All right. So 1 sends to 2, sends a request, ID number 1, sequence number 1, destination sequence number 1, hop is 1. And at the recipient, 2 things happen, which means number 2. At node 2, 2 things happen. First of all, it says, oh, this is a new request. Therefore, I should broadcast and record. Broadcast is here, record is here. What does it record? It records that the destination, now here it's recording destination as 1. Why it is recording destination as 1? Because this is the reverse path it is recording. Right now it has no information about 10, but it knows that the best path to 1 is through 1. Okay, which is sequence number 1 and hop number 1. So now let's see what is the sequence number 1. You see the source sequence number 1 is 1. Right, so this is the, for the destination 1, its sequence number 1, I am at 1 hop away, and the next hop is 1. This should be clear. There are 4 ones, but they are all being initialized because they are coming from 1. If I were starting at 2, some of these will be 2. But it records 4 things in this table: destination, sequence, hops, and the next node. Then 1 sends to 3. 3 does exactly the same thing, and 4 does exactly the same thing, but all of them broadcast. So now 2 is going to send to all its neighbor, 2 is going to send to 1, 7, and 5. Just see. 2 is going to send to 1, 5, and 7. I have put, generally just to keep life straight, so that I don't forget anything, I just go clockwise. So I started 1, 7, and 5. You could go either way. You could go just 1, 5, and 7, just numerical order, as long as you don't forget some neighbor. So 2 to 1, 2 to 7, 2 to 5. And all we do is increase the hop and we send. Now 1 gets it. 1 says, I know this request, so I'm not going to do anything. So it discards. And then 7 has not seen this before, so it makes a note. Okay, actually it probably makes 2 notes. I did not put all the notes here. It makes a note for 1, it makes a note for 2. It could make 2 notes. Actually 2 it probably already knows, but it makes a note that to get to 1, sequence number 1, I am 2 hops away and the next node is 2. See, for 7, to get to 1, the next node is 2. Then 5 does the same thing. Now 2 has finished. Now let's see, 3, now we'll get to 3 here. And therefore I draw a big line at hops. So now I have to repeat 2, 3, and 4. I just finished 2. Now I have to go to 3, find all its neighbor. I have to go to 4, find all its neighbor. They will all have the hop count 2. I finish all of these duplicates and all that. Then I go 1 hop more now. We have to go to 3rd hop. Before I go to 3rd hop, I make a note of the nodes that I want to broadcast in the 2nd hop. So the only thing they want to broadcast is 7, and here is 6. Right? So then I make a list of 7, 5, and 6. Actually 7, 5, and 6.
So the action at recipient, basically there are 2 actions in the top row.
Yeah. Yeah.
RF is a unicast to the last node on the backward.
Okay. There is a bug right there. Just global replace rrec.
But there will be an RF.
No, see, this is rrec right here, right? So new rrec. If you are reading on this column,
New RF broadcast to neighbors, right?
yeah, this is a new rrec, and therefore, no, so it's not prepared. Okay. If your question is,
Deploy.
this is just a realization that this is a new request, and therefore I should broadcast and record. New rrec. And I did this in Excel, by the way. That is the easiest way. It's just way to do to add rows and tables and columns and things like that. So just for your help. And so yeah, so there is a mistake here, rrec. So this remains rrec all the way up to here. This is rrep here. This is the reply coming back at the end. So going back here, one more thing I found helpful was that you really what you're doing is you're going hop by hop. So first you started with 1, you finish all the first hop nodes. So 2, 3, 4 were in the second set of lines. And then you go to third hop, second 2 hop nodes, which are 7, 5, and 6. You see here 7, 5, and 6. Right? Then you go to 3 hop nodes. That would be 9, 8. So you go here and you find 8 and 9. Right? And then 10 and backwards. So that way you remember that you didn't forget anything and all the rows are there, things are there. It's a little bit, basically complicated, easy to make mistakes, but it's good to do at least once in life. So this is, you think you can prepare this up to this far so far, then I go to RREC. Any question about RREC? Yeah?
I don't really understand the last column.
The left column?
The last column.
Last column. Okay, so last column is actually this table. So each node keeps a table which says, no, this is not the table, sorry. Table is this one. This table. Remember, some columns of this table are shown. To go to the destination, whatever destination, what is the time that I know the path, how many hops away it is, right? And then what is the next node? So let's go back here. These are actually 4 columns. Now here is what I could have done. I could have put 4 columns here. It's just there was only so much time and so many things. So basically, so the first column is destination, second column is the sequence number for that destination, third column is the hops, and the fourth column is the next hop, and next node. Right? So let's read in the middle here. So this one says that if you ever want to go to 1, if 5 ever wants to go to 1, it should go to where? Sorry, 5 should not go to 1. Sorry, the 9, sorry, this is for this one, recipient 8. If it ever wants to go to 1, it should go to 5. Because the next hop is 5 and the cost is 3 hops. So let's just see here. If it ever wants to go to 1, it says that the cost is 3 hops if I go through 5. Now, you notice right here the problem. Problem is that 8 could have gone through 6, 4, 1. That is also 3 hops, equally good path. But it doesn't remember two lot routes. It just remembers 1 for memory saving. So, both of them are equally good, so you just keep 1. If you find better, then you override. Okay? And so, there is only one path is kept. So 8 will record that one. Now, the thing is, whenever you broadcast, so you have to repeat, right? So we finished 8, 9. Now here is, once finally it reaches 10, which is right here, 9 sends to 10, it says this is a new request. And now I got to remember this, that I have to change request. But now it sends a reply. It sends a reply and it says my time is 6. Now 6 is just a random number I drew. Okay, it could be any time there. It is better than 1 for sure. It is better than 0, right? So just any number here, and I think I should probably just let you use 6 also, because when we get the homework back, everybody has a different number, we would be very confused. So just use 6 for the time being. Okay, but it is a random, just some time. So it says my time is 6 and okay, now you see here the hop number. So what happens, this is a new message in which your previous message is encapsulated. So your request is there, but now this is a reply. Reply includes the request plus this new thing which will discover the path in the backward direction, or which will follow in the backward direction, right? So this is an interesting thing is to see that this one says that I'm, basically 1 hop away from U9. So now 9 is the destination. It will remember that to get to 10, the time is 6. It is 1 hop away and the next node is 10. Right? 9 will send it to 7 7 will increment the hop count, and it will remember that to get to 10, time is 6, hops are 2, and the next node is 9. Right? 7 will send to 2, and so on and so forth. Yeah.
The last row should have hops before, right? 4.
Okay, the number of hops is equal to the number of dashes. So let's see. Somewhere, number of dashes plus 1, is it? Number of dashes. I was thinking everywhere I noticed 1, 2, 3. 1, 2, 3. No, sorry. Oh, too much confusion. So this is everywhere there are only 3 dashes in this case, so there is no problem. Yeah. So dashes don't mean. Now let's see how many hops are here. If it is 1, 2, 3, this would be 4. Alright, now here's the thing. Please make sure that you understand our ask right now. We still have 5 minutes because this is the homework. For this example, there is a homework number B, 13B, which will be due next Monday. So if you have any question about this, ask right now before we move forward. Any of the columns, rows, numbers?
It's still the 6 is the arbitrary number.
Yeah, 6 is the arbitrary number. 6 just happens to be the time. Actually, I could probably make it a standard number by saying that each of these is 1 unit of time. So first unit this, second unit this is third unit, this is the fourth unit, so this is the fifth unit. Something like that. In one slot something happens and it goes one more hop. So we could make it, but it just happens to be, whatever timer happens to be the value there, it just puts that number. And it doesn't have to be a global number, it is just the number at that node. Right? So while you have 6, I could have 3. Yeah.
So the row from 9 to 10, the action recipient to the new R class as well.
Okay, so let me see. You are saying on this line, 9 to 10. So this explanation of the recipient. Number 10 says this is a new request. Request, I should respond. Here it doesn't say respond, it says just broadcast. New request and then response, so this is the response comes back.
Yeah, I mean, that should be RREQ.
So that's what I said, there's a bug here. Everywhere it should be RREQ. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 places it should be RREQ. Alright, you have the big table right there in front of you. You can correct in that one if you like better, because microprint may not be readable. I wasn't sure, so I just printed both. Any other question about this? Alright, this is not in any book, by the way. The book actually which is referenced here, let me get to see, I couldn't find a place to put the book reference. Yeah, here it is. Okay, this is the book, Kumkum Garg. And so this book, this came from that book. Actually, that book is the best book for you to read, and you should read, because every book I'm selecting here are Safari books. So you can read it at home anytime. It does have examples, but it needs lots of graphs. It just goes step by step on each graph. And then, basically, it doesn't give complete, it just gives a few examples that, okay, 2 will do this, 3 will do this. And I just wanted to make a whole list just to see that I can make the whole thing. And so I ended up doing this whole table. Alright, feel comfortable? Alright, so now I'm just going to finish AODV, we still have a few minutes. So it is not just for unicast, you could also find out multicast. So you could find out where all the routers are. Remember the broadcast things? So you could send a broadcast route discovery, except that what happens is, which is your destination? So now there are 5 destinations, right? If you're not the destination, and so then basically you just forward. If you are the destination, you will respond. So there will be 5 responses, right? So If a node receives a request, it is not a member, does not have the route to any member, it creates a reverse route entry in its table and broadcasts to neighbors. If node is a member of the group, it sends a reply to the source and forwards to the other neighbors. So you still forward. Right? That's the only extension. So intermediate node make a note of all this. So now they have many paths to the destination. So for multicast, you know, if I get a route message to all routers, I will send it to this and this, these two, not to the other people. So here we have to keep multiple paths. For other nodes, we just keep one path. Here's an example. Blue things are request and red things are reply. So A will broadcast to both B and C. C will broadcast to B, D, and E will broadcast and so on and so forth. Some arrows might even be missing here, I don't know. But then the D and E are members. So D will send a response and E will send a response, and B and C and A will record it. Now what happens if there's an error? So if you don't reply, then you are no longer a neighbor. So hopefully you are a neighbor, and then if you cannot send anything, then at that time you send an error message. Error message is sent if the packet transmission fails or if the hello doesn't get through, and it contains the destination sequence number that was failed. So when somebody receives it, they either try to get a new route if they need it. Otherwise, you know, you just basically know that this information is out of date now. All right. So the error message is sent back. All of this is explained in RFC 3561, which is pretty old RFC now. But that finishes our AODV. Next time we will begin on DSR. So the homework 1, 13A, 13B are already done. 13C is on DSR, which is somewhat repeat of what we have done today, but we'll do it next time.